York office, and he's going to talk to us about how the water affects the rail and knowing your enemy. So, over to you.
Thank you very much. Hi everybody, my name is Iain Fox. I am Senior Design Engineer for Network Rail. So I work in the design side of the business as opposed to the routes or the regions. My background is in water management, so drainage design, flood risk, hydraulic modelling, and scour risk to structures. I am one of Network Rail's, scour experts. So I work on a national level. I don't sit within any route or region. I cover pretty much from north of Scotland all the way down to Penzance, and literally everywhere in between. So I did a very similar talk to this for the ICE just before Christmas. I was asked to come down to see you guys here and give you a very similar presentation. Looking at water and how it affects the railway, we know it's very prevalent in the news. We know climate change exists, so how and what is it that we're actually doing? There is a plan for this evening, believe it or not, so this is it. So we're going to have a look at the difference between a drainage engineer and a water engineer. That'll make itself clear in a sec. We'll have a very brief look at Network Rail management process. I don't want to put you all to sleep, so we won't do too much on that. We'll kind of concentrate a little bit on what the issues are. So the main issues of climate change, the main issues of existing and aging infrastructure, and the issue of scour bridges and structures. We'll have a look at what we have within Network Rail to try and fight this water. We do have a water management strategy. Excuse me. We'll have a quick look at hydraulic modelling, and we'll have a little look at catchment analysis as well. And then we'll finish off by having a look at some of the advancements that we are pushing to try and help us manage this problem. So if I start by looking at drainage, and if I say I'm a drainage engineer, it brings up certain connotations in your brain about what my day-to-day job is. And most people think that we deal a little bit with some crest drainage. We have a look at, that worked well. We have a look at some counterforts. We have a look at the cascades to bring the crest drainage down onto the track drainage. And you pretty much think that is my day-to-day job. That is a drainage engineer's job. If I go into schools and colleges and ask them the same question, pretty much that's what we get as an answer. If I then open that up and say, okay, forget drainage engineering, I'm actually a water engineer. Now what does that tell you that I do? What that tells you is, yes, we deal with track drainage, and we deal with catchment analysis, and we deal with the hydraulic modelling, and we look at third-party inflows, and surface runoff, and flood risk management, and riddle flooding, and tidal flooding, and scour. You get the idea. And we also look at some research things.
What do you do in the afternoons?
The afternoons are just spent sleeping, really. It's, but as a Network Rail drainage engineer, this is actually what we do. And there's a labelling problem between what you think we do and what we actually do. And Network Rail very kindly gave us this little graphic, which I'll make a bit bigger for you actually so you can see. Kind of demonstrating the water use and problems around the railway. So if we just pick a few of them. So yes, we operate drainage assets to take surface water from the railway corridor. How many people know that we actually are responsible for managing water quality off the railway? We can't pass forward contaminated water. We have legal responsibilities around discharge. We manage coastal defences. Network Rail have got several assets that are classed as coastal defences. And those defences don't just manage the railway, those are coastal defences for properties, towns, villages, and beyond. We use water, obviously, dust suppression, cleaning trains, things like that in the DUs. We dewater tunnels. We use potable water in the stations. We prevent scour. We manage flood risk. All of these things go on to my desk and my day-to-day job as a drainage engineer for Network Rail. Does that come as a surprise to anybody about what the scale of what it is that we do, or am I preaching to the converted? silence. Brilliant. I love a bit of interaction. Okay, we'll move
Well, I
on.
think a lot of things have become much more, if you like, the traditional view of the drainage engine in managing drains. The environmental issues and climate change have made it much more than
Absolutely.
that in recent times, yeah.
And when we come on to look at catchment analysis and problems, we'll touch on climate change to get a bit of an understanding of
It is getting more difficult to defend our position with coastal assets, protecting the communities.
Yeah.
It's solely for supporting the railway, but that's becoming more and more difficult to defend.
It is, and it's an argument with NRW. It's an argument with here in England, SEPA in Scotland, that all the routes and regions are having about maintaining these flood defences as flood defences and not just as a railway, because there's a huge cost implication in defending or keeping them as flood defences and not just keeping them as a railway.
Because we're not a coastal protection authority, are we?
No, but we do manage coastal defences.
Yeah.
There are quite a few, actually, quite a lot of them in Wales that don't get into trouble.
You got a few.
Yeah. So as a network rail, yes, we've got a management process. We've got one for everything at the moment. The drainage one happens to be SIP 005. It looks at things such as all of those things. So it looks at things like how do we evaluate a drainage system? If we know a drainage system is in the ground, how do we evaluate that? How do we describe the assets? How do we look at management plans? How do we inspect a railway system? How do we maintain it? How do we design it? How do we install it? All of Civil 5 comes all of these things. The reason, as far as I'm aware, that Network Rail take this stuff very seriously is this. Flooding pretty much is the only thing that gives Network Rail negative headlines. What I mean by that is, if you saw recently the vehicle in Manchester that went over the parapet on the rails, the headlines, the news was Network Rail work round the clock to get trains moving again. If we have an earthwork failure, Network Rail engineers work through the night to open the line for millions of commuters. Flooding tends to be the opposite way. So flooding tends to be Network Rail cause misery for millions. And just some of these, rush hour trouble for commuters, it's all negative language. Severe flooding disrupts trains, transport disruption, in inverted commas, will reduce delays, because the press never believes when we talk about what. Flooding compensation costs revealed. It's all negative headlines when it comes to flooding and when it comes to water around the railways. There's very few positive stories that says Network Rail built you a new river. Doesn't happen. So this standard tries to prevent these. Whether it works, well, we're working on it. So climate change is one of the biggest challenges that I think we all understand is happening. It is getting wetter, it's getting warmer, the river levels are getting higher, the velocities in the rivers are getting more, the amount of water, the volume of water coming down there is huge. If you look at the Environment Agency, Natural Resources Wales and SEPA, they all have estimates on 2050 and 2080 river levels. And some of those are adding 100% extra flow to what you have now. So if you've got a river, it's going to double under normal conditions by 2080 in some of the predicted models.
Winter time flows.
So it's a
year round.
flood model.
Yeah.
Yeah. So the flood is going to get a lot more because the rainfall gets heavier, catchment drops all that rainfall into the river, and that response is over 100% in some areas. I've seen 124 in one area in Cumbria, which is enormous.
Does that take account of 1.5 million new homes before the end of this government? Or is that?
No, doesn't account for those. Again, obviously, one of the use cases is you put more homes on, you get much faster runoff, and it changes the response time of the catchment. It doesn't change the volume of water, it changes the response time of the catchment, so the water gets to you faster than it does now.
What I call the flash flooding.
Yeah.
Flooding risk.
Absolutely. Dry ground that doesn't infiltrate water, it perches on the top before it gets a chance to infiltrate in the ground. So you've already got increased water in your ground, and you've got a saturated ground, it does exactly the same thing. The water's got nowhere to go. So just
This is Wales, the ground is saturated all the time. As soon as it's saturated, the water just goes straight off the top.
I am saying nothing. So, as Network Rail, we do have a weather resilience climate change adaptation strategy. If anybody is bored enough, feel free to scan that QR code and it will download to your mobile device the entire plan. If you cannot sleep on a night, that's brilliant, brilliant document to get you to sleep.
There's a lot of it.
It's a lot of it. I will come on to that in a second. The next slide has some key points from it, so I won't make you read it all and come back next week and tell us. And here's the interesting stat. When we're looking at climate change, I know we're talking about flooding, but just have a look at this one. Heat plays a part. During July 2022, there was a big heat wave, certainly in England. And it reduced train performance by about 40%. Now, the way it does that is a lot of these power supply buildings overheat, the transformers overheat, and they're a big tin shed. And when the sun beats on them, things just pop. And if you don't get air conditioning units inside those PSPs, things will go pop. We couldn't get enough in, and in July 22, we dropped performance by 40%, which in 1 week caused a £30 million loss of revenue for the railway system. That's a lot of money, an awful lot of money for heat. Can you imagine what flooding is? Big numbers. This is an interesting one. So I'm not telling you where, but there's a major city in the UK that predicts one of its rivers is going to have about 78 million cubic metres of water additional to now by 2080. For context, that 1.5 mile long, 120 metre deep lake holds 78 million cubic metres of water. That's additional to what that city gets now by 2080. Where is that water going to go? How do we deal with that? I haven't got the answer, by the way. The answer is not next. I haven't got a clue. That is an awful lot of water for one city in one part of the UK. By 2080, the predictions go the way they're going. It's an awful lot of water. There's a calculation done that if you look at Ullswater in the Lake District, which is what, 8.5 miles long, I think it is, that would have to be about 10 metres deeper than it is now to accommodate that water. A vast amount of water. Difficult to picture. Yes, we've got lots of aging assets and infrastructure. Around 90% are as they were when they were installed about 20 years ago. Some of the structures Brunel built. What was that? Out of 1800s to 1850s, 1860s. A lot of structures actually are more than 150, 200 years old. They weren't designed for the amount of water that's coming down the channel now, let alone in 20, 30, 40, 50 years' time. How do we solve that problem? There's actually quite a lot of European funding and European money going into that problem right now. A lot of research projects going on by a lot of universities trying to work out how to manage existing infrastructure through climate action, climate change. And drainage assets. Most of the drainage on the railway was probably installed 10, 20 years ago. And some would argue it hasn't been touched until we put in the ground. That's not the big comment on. However, if you do a hydraulic model now based on drainage that was put in the ground 10 years ago, it will fail. It hasn't got the right diameter to take the additional flow. And as we were talking earlier on about housing estates, that's where this comes in. If you've got houses built around the railway, which people build either around a railway or around a river, that's where people build. All of that runoff gets to the drainage system a lot faster than it used to, which causes your pipes to be full of nowhere, which causes surcharge at the top, which causes flooding on the track. Let me close the line. Quick look at scour. Scour is the largest single cause of structure failure. For those who don't know what scour is, it's the action of removing riverbed material due to water action, hydraulic action. Erosion, essentially. Cost Network Rail around about 100 million per control period. That number is from the technical authority, not from my brain. And again, it's an increase in risk. As we say, it's not the riddle level that causes scour, it's the energy within that water. As the water increases, naturally it gets faster and faster. So it is a huge problem. We'll look at scour in a second. This is the climate adaptation snapshot. So as Network Rail, we own about 20,000 miles of track. We own about 30,000 bridges, tunnels, and viaducts. Countless numbers of signals and level crossings, and we do manage 20 of the UK's largest stations. The Schedule 8 cost, for those who don't know, is what we pay to the train operating companies if we close the line unexpectedly. So when you're on a train, you get delayed, and you rub your hands together because you can get your delay repair, that comes from us. So please don't claim it anymore, please. But these some of these numbers, these are from 2016, these numbers. So wind has cost us 382 million since 2016. Flooding has cost us 316, and earthwork failures 144 million, just in Schedule 8 costs. Not remediating the problem, not fixing it, not doing anything else. That's just what we pay out to the train operating companies. You can look at that one on your own time. This one's interesting. This one's the investment that Network Rail are putting in CP7, which is what we're in now. Earthworks and drainage account for about 1.8 billion of investment in CP7. That's how serious Network Rail are taking water management, flooding, scour, etc. Broken down by region, a primary asset or a primary function is one purely designed to combat the effects of climate change and water. The secondary part is a scheme that was already going ahead that has the added benefit of improving weather resilience. Wales and the Western, for primary resilience, £409 million. CP7. It's an awful lot of money. It's an awful lot of zeros, and I would love the interest even on it, never mind the money itself. It's an awful lot of money going into this. As I said, that I will go back to that snapshot of the QR code if anybody wants to have a look at that a bit more in depth. So this is scour. Give you a bit of an idea of how it happens if you don't already know. If you know, please just stop me and I'll move on. It's all to do with the flow dynamics within the river. It's all to do with how the water interacts with the structure. Even a nice cylindrical pier like this causes mass scour. You've seen this, you've probably been on the beach, you've seen the erosion around piers and structures on the beach. That is exactly what it is, it's scour happening. If you see this little standing wave at the front of a structure where you've got constriction scour, absolute sure sign that something's happening underneath that riverbed. You don't know what, you don't know how bad it is, you don't know if it's protected or not, but I certainly wouldn't be walking or driving across a structure when you see something like that happening. And it's to do with, as I said, the velocity and the dynamic flow within that river. Structures affect the way these things work. An aeroplane wing is the exact thing of what you're seeing on screen, but with air rather than water. It affects the dynamics, it affects the flow paths, and it causes turbulence. When you get turbulence, you get eddy currents, you get an increase in velocity, and you get magnitude and being spread down. To try and give you an idea of what that looks like, this is a computational fluid dynamic modelling. This is from Penn State University. What you're looking at is the flow rate that's going to come down there. You're not going to see the water. It's been made invisible for this, but you're going to see flow rate coming down here. You're going to see a flat and level bed, and we're going to see what happens as the bed becomes mobile. The blue area is about 1.3 centimetres on that scale. Let me try and run that again.
Introducing.
Oh, yes, there we go. Try and pause it a second. Pre-progression. Right. What we're seeing is, from the previous slide, is seeing that vortex shape start to take shape. The reason that you get more scour downstream is because the eddy currents roll before they actually get back into normal flow. You've also got constriction scour, so very similar to your hose pipe in your garden at home. You turn the tap on, you're watering the plants, the kids or the grandkids come into the garden, it's the law that you squirt them with the hose pipe. What do? You put your finger over the end, don't you? You don't turn the tap up anymore. You put your finger over the end and you squirt. Q equals V here. So flow rate equals velocity times area. You reduce the area, the velocity has to increase to keep that formula constant. Exactly what this is doing. We're now on the riverbed. Granted, only by a small margin, this one. We can imagine where we've got a big viaduct. We've got maybe 2 metre wide, 3 metre wide abutments up here. It's a huge construction. So yeah, I'll skip forward on that. See, it's called. No, I'll skip forward. There we go. So, what have we got to help the fight? Network Rail do have, as we said, the water management strategy, and I'm going to let her explain.
Introducing Network Rail's water management strategy. This strategy is going to change our approach to water management. But before I tell you more, this is why we need it. Climate change is happening now, making the consequences of extreme and adverse weather a reality for all of us. Flooding and droughts already cost Network Rail millions of pounds a year and are only likely to get worse. From landslips to electrical failures, weather-related incidents affect the safety and performance of the railway, resulting in penalties, delays, poor environmental impacts and a disrupted service for our passengers. But we can improve. Network Rail is committed to running a reliable railway network. To do this in today's world, we need to prioritise water management. This means dealing with the water that affects all of our railway assets. We need to grasp the wider challenges of water scarcity, polluted water, and the potential benefits of excess water, in collaboration with our neighbours. We've developed the water management strategy consisting of 5 principles. These are: take a holistic view, be resilient, use less and recycle, keep it clean, and unlock wider benefits. We are the first in the transport industry to develop a water management strategy. It's an opportunity for us to demonstrate our proactive leading approach. As the 4th largest landowner in the UK, we can make a profound impact. Water affects all of us on the railway. Every asset group and all life cycle activities, including inspection, maintenance, design, construction and asset management, have a part to play. We all have a responsibility and we need to start today. So, how do you make a difference? Start by engaging with the water management strategy. Go to the My Connect page for more information.
Another QR code, feel free to scan. We will, however, have a quick look at it. So, water management strategy on a page. As I said, there's 5 key principles of this. Take a holistic view. That is one thing that Network Rail has been terrible at over the past 20 years. What I mean by that is we've looked at our drainage system and we haven't looked anywhere else. Most Network Rail drainage systems have inflows. They have third-party assets coming in. We've got surface water coming down to it. We've got surface runoff. We've got fields surrounding the railway that transport water down. For 20 years, we've ignored that. We've just gone, no, our pipe is here and it works perfectly. Doesn't inflows. So that holistic view is having a look at those wider areas, those wider catchments. Be resilient. Be prepared for too much water. So do we now design with today's flows in mind? No. What we now do is we add climate change allowances on and design for those flows. Be prepared for too little water. Doesn't affect the drainage side, really. But certainly if you're using water in a DU or a train depot, you need to try and think about, try and use less and recycle, which is the next one. Can we actually capture that water? Can we capture rainwater to flush toilets, for example, in stations, which is happening now? Can we recapture other types of water? Can we reuse it? I don't know, possibly. Keeping it clean, as I said on one of the very first slides, we have a duty of care, we have a legal obligation, to make sure that water that we pass forward into lakes, rivers, even into utilities, is clean. We can't be passing hydrocarbons forward, we can't be passing polluted anything forward. All of those should then go to unlock the wider benefits. If we can start to save water, use it more responsibly, it should mean there's actually less water in the system going round in circles and increasing with climate change and actually relieving stress a little bit on our assets. It's not just me saying it. Andrew says it as well. Water management is the most underrated discipline, or has been certainly for the last 20, 25 years. I think it's no secret that any scheme, any renewal, when it gets tight on time or budget, drainage was always the first thing that was pulled out. It's the thing underground, nobody sees it, nobody cares about it till it goes wrong. That was the mindset. Thankfully, that is changing now a little bit. We're not quite there yet. And Mona, who's our technical lead for drainage in the technical authority, says water goes beyond drainage. So that comes back to my very first point of, is it a drainage engineer or am I a water engineer? I think the name is irrelevant. I think it's the job that you do is the relevant part. It's what I'm called doesn't really matter. Again, you can read those, they are in the water management strategy. So how then? We've talked a little bit about catchments, and we've talked a little bit about how that water interacts with us, how that gets there, and I'm going to let her explain again.
Surface water runoff has potentially devastating consequences to the railway. At Network Rail, we need to manage this threat across our infrastructure to ensure we operate a safe and reliable service. This is why dependable data is so important. It helps us to make the right decisions to protect passengers. Now, for the first time ever, we have a data set that maps rainfall catchments across the entire railway network. It's taken more than a year to produce and encompasses more than 100,000 individual catchments, taking into account various catchment characteristics, from catchment area to soil type, in order to understand potential surface water runoff. This dataset can provide the likely amount of surface water runoff flowing towards the railway from each catchment for a given rainfall event. It relies upon the Flood Estimation Handbook, an industry-standard statistical model developed to understand surface water runoff peak flows from UK catchments. While the methodologies used aren't new in themselves, this is the first time we've been able to access this information for the national rail network at the touch of a button. The dataset is available as a map layer in GeoRNM Viewer. A water threat index derived from the Flood Estimation Handbook model and other critical attributes such as crop cover and catchment slope provides a colour-coded ranking for each catchment. At a glance, the user can understand the catchments that potentially pose a surface water threat to railway infrastructure. This helps asset engineers swiftly decide which assets need improvement first and where to install new drainage systems, making budget allocation easier and enabling rapid comparative assessments of which catchments are potentially more troublesome. Now it's possible to view a section of track online and contrast the relative hazard posed by adjacent catchments and how these compare with other catchments across the network. The dataset also provides a great starting point for more advanced analysis, assisting asset management teams and designers in making informed decisions and facilitating good engineering judgment when developing new capital schemes. In addition, the dataset is also being used to build new asset management tools currently under development, such as the Streams tool. When used in conjunction with programs such as this, the dataset has the potential to help provide a complete drainage system overview from inflow to outflow. This allows engineers to understand the current and future ability of drainage systems to protect the railway in the years ahead.
So much better than I could. There's a couple of key words there, and it was potentially can do all of this thing. It's very much a starting point for a greater look at catchment. Catchment analysis has its own degree course. That's how complex that is to try and work out where the water comes from and where it goes to. This is a very, very quick, light touch version and is designed for the routes to be able to try and prioritise or get greater understanding of how the water works and then pass it on to the hydrologists and the hydraulic modellers to actually quantify that risk. But it is something that we've never had in Network Rail before, and it is something that is has got the potential to be very, very powerful at a quick glance to try and prioritise things. I'll have a quick touch on some hydraulic modelling. I guess most of you understand or know what hydraulic modelling is. It allows us, there's two types. So we've got a drainage hydraulic modelling, which you can see in the top corner, which is where we can build a 3D version of the drainage system that we're installing. We've got the gradient pipe sizes, catch pits, everything, and we can drop some rainfall on that and see how that system responds. Is it big enough? Has it got the right slopes? Is the outfall sufficient? And we can test varying degrees of rainfall, we can test surcharge, we can test flooding, we can test all sorts of things, we can stress test it. We can build it for existing systems and stress test the existing system. There's a project near London at the moment where we're trying to map about 3 miles worth of drainage so that we can actually model those systems and see how they respond. Is there blockages, is there damage, is it just not big enough, or is it fine? We can also look at things like river modelling, which we use for scour. So this is a free piece of software called HECRAS, developed by the American military. It's regularly updated and will always be free, thanks to the US government. It's a backwater effect model. What I mean by that is you need more cross sections after your structure than you do before your structure, despite the fact that you're trying to work out what the water's doing before your structure and not afterwards. I think that was sufficiently confusing. Excellent. What it means is the things downstream have a greater effect on your structure actually than the water approaching your structure. The water approaching your structure is quite easy to guess or to predict. What happens after the structure, people generally forget about. But if you think about how a weir works, we put a weir in the river, it will deepen the water. And what you will actually get is from the top of that weir, you'll get a flat water surface right the way back to wherever the river gradient is. That's called the backwater effect. It does have a pretty profound impact. You can get these channel average velocities, so each of those colour-coded lines actually represent a different velocity through the watercourse. What you're hoping for, the reason I've included this one is because it worked, what you're hoping for is the darker colour is a faster water flow, and that's where the deeper riverbed should be. And in this case, it did work. So we can predict in a 200-year flood event, and we can see what those velocities are. There is now a 3D CFD model, which you saw for the scour piece earlier on with the 3D modelling. That takes it to a whole new different level, and we'll touch on that shortly. You heard in the video about streams. I just thought I'd quickly touch on streams. So this is drainage and line site tool that it's what we should have had 10 years ago. And what I mean by that is it's a one-stop shop for everything to do with your drainage. So it's got your catchment details in, it's got things like your workbank management tooling, it's got all of the historic data in, it's got catchment stuff in, it's got rainfall data in, it's got all sorts of stuff that allows you to sit and look at one program and see what's going on without having to have 10 different logins for 10 different systems, as we've always had. And it tries to bring them all together. And Mona is very, very passionate about this and pushing this to the roots. It does all of your KPI reporting and everything. It's a very, very good tool. As I said, the catchment part of it is a starting point, but it's in there as well to try and help you understand what's going on in your area. Right, bear with me on this. This could get a bit dry. Right, we're looking at using L-band radio waves. So L-band is a long wave radio waves. There are currently 2 satellites above us, opposite poles of the Earth. They rotate around the Earth as the Earth spins. Very similar to Radio 4, which I'm sure you're all familiar with. You can still listen to Radio 4 sat in your living room. Those radio waves penetrate your walls and get into your house, and you can hear it. Brilliant. These L-band radio waves penetrate the Earth to depth of about 3 meters. The response that the satellite receives from that signal tells you how saturated the ground is, because you get a different wave pattern coming back if it's dry ground compared to if you have moisture present. What you actually end up with is a very noisy section of the railway corridor. Green is good, yellow's okay, red is there is water there. Now, you could be looking at wet beds, you could be looking at broken drainage, you could be looking at an aquifer, you could be looking at all sorts of things. We process the data, we don't process the data, Astro do. The data is processed to give you a bit more of a heat map, and then it's processed again to actually tell you where your problems are in terms of groundwater. Thames Water use this to detect leaks within their drainage system. It's about 97% accurate. Each one of those squares, one of these squares here, is about 3 meters. So this company can tell Thames Water within about 3 to 6 meters of where they're digging for a leak in their system. We're kind of trialing it at the minute to see whether it works on the railway corridor, so we can see wet beds, we can see all the drainage, we can see what's going on if we've got particular problems. Give you an idea of costs, because why not? If we were to map all of Weston's drainage, all of Weston route, so that's Paddington down to Penzance, it's about 300 grand for the whole route. That gives you access to all the historical data as well. So every time that part of the earth passes through the satellite, you get an image. So this company will actually look back through the archives and try and compare and contrast different times of the year and different, how it's behaving over time. Not cheap, right? Yeah. But if you can pinpoint things like, we know there's a drainage leak here or a wet bed here, we know the wet beds, we can see them. But if there's a drainage leak, it's very, very easy now to actually dig up there rather than digging up a 30, 40, 50, 60 metre section looking for it. So yeah, that's one of the advancements that's coming in. It does work day and night, so you actually see the moisture. It is Fox by buildings. Satellite is however many kilometres up in space. The Earth doesn't pass directly below it very often, so it's quite often looking on an angle. Central London's a nightmare for this because you can't get through the buildings to actually hit the floor. Rural parts, if it happens to be vertical, brilliant, you can get some good results. So it's not an exact science, but it is a very clever science.
How long would it take to get a result from something like that? Say you had a block, you knew you had a block drain.
Yep.
But you didn't know where it was in that 50 metre run.
Yep. So assuming
how
that
quickly could you get a
14 days. So assuming that the satellite has gone across now, we've not asked it to look at the area because we have to divert the satellite. So it could be this side or it could be this side. The satellite is just going straight line. So assuming it's just gone past now, it'll be 14 days with the Earth rotation and its rotation to be back on the same spot again. We can ask it to look left or right. Bit of post-processing, you're probably talking 3 weeks if it's an emergency or a
right. But it only looks at what you ask it to look at.
Absolutely. Yeah.
Oh, okay.
It will look straight down, but if you want it to look to the left or the right, you have to go on the satellite, alter its tracking, turn the satellite so it looks in the area you want, and then it'll track it across, and it'll get those readings for you. And it's a 14-day cycle. So 14 days maximum to get the raw data, and then probably a week or so post processing to go from that.
It's a long time to have your track closed because it was flooded.
It is, but it wouldn't be a reactive tool. That would be a planning tool or a proactive tool. You
I
would
think that's the benefit to make that you can see water in the ground. So if you've got a leaking pipe, if you've got a blocked drain and it's starting to spread, you're going to see it before it manifests as actual flooding on the ground.
absolutely. What you're going to have is, if you've got a wet bed, it doesn't say that the problem is here. What it says is the wet bed's here, but actually the leak could be 30 metres up because the ground profile and the track bed is actually migrating down the low spot. So you'd be able to track where that water comes from and where the source is. So you wouldn't be digging here going, well, it's just groundwater, there's nothing here, but you could actually dig up there, dry it out. And then, it's not for every use case, don't get me wrong, but it is a very clever advancement. You can use it for earthworks, so you can actually look at saturated earthworks. You could you? No, you could. So what you could do is look at a 5-day ensemble weather forecasting and try and predict where the rainfall is going to happen, and then try and have a look at how saturated that slope was last time we went through. If you've got a particular flooding site, that you know that slope is moving, or you know that slope is particularly wet, and you could try and predict.
Yeah, I bet the Southern Valley Railway wishes they had something like that, the original one.
Yeah.
Or we did it wherever it is at Norfolk Midney. So instability.
Along the cliffs, yeah.
If you do a small section, you probably, I'm going to make a number of about 50, 60 grand. I would imagine do a small section. But as I said, you could do a full length, a full route of attraction. The grand scheme of things is probably really good.
No, it's interesting because we already use soil moisture deficit to predict track geometry. This sounds like another step up in providing that kind of information.
Absolutely. Yeah, absolutely. I'm just conscious of the time because it's already 6 o'clock. This is something that I'm currently on with Western Route, funnily enough, which is looking at real-time scan monitoring using bits of artificial intelligence. So the actual clever bit isn't me. The clever bit's actually the camera that sits and looks at these assets. It uses a difference model, so it will look at the picture it took last compared to the picture it took now, and it will tell you the differences. So it will tell you whether there is deposition of the bed. So have we got an increase in bed levels? Have we got a decrease in bed levels? Has the structure moved? Has a badger walked in front of it? It'll tell you all sorts of things that you asked it for. The clever part is it knows what a badger is and won't alert us because we don't care. It will alert us if this structure moves. It works pixel level. So if that bridge moved 3 millimeters, it would alert us if we wanted it to. We probably don't because as a train goes across it, it probably moves more than that, I would imagine. Actually, we don't because I don't know what size this. I have a picture I might show you later on. But there's a person on it about that big, put the marker board on, it's tiny compared to the bridge. That's in Bristol, I would if anybody recognises it. So a good sign. So we've got the camera. The camera's looking at above water level and the structure itself. We've got some flow sensors, uses ultrasonics. They're mounted in the river itself, looking at real-time velocity. So we're moving away now from the predicted hydraulic model, and we're actually measuring real-time velocities in the river and at the bed. And then we're looking at some kind of, I can't go into it too much, but we're looking at some kind of GPR / EMT type of riverbed monitoring to actually look at the physical bed and see that scour ball moving or forming and infilling as it happens. It all runs on 12 volts, so it all is run from solar panels and batteries. The reason that we're doing that is because probably 90% of our structures are not in the central London with a plug socket right next, which is very sad, but that's just the way it is. So we have to use renewables to try and power these things. We're using it on 3 structures at the moment. There's one in Bristol, which is that one. We've got one in North Devon, which is north of Exeter up on the Barnstable line, and we've got one in Windsor on the branch line in the station. Huge 50-metre span structure now, and it's the River Thames, and it's navigable, which is causing a few issues, I'll be honest. But yeah, that's kind of trying to look at bed evolution over structures and trying to get that real-time data to let the routes and the regions make better decisions based on real information. And you'll be very pleased to know that that is about me. We've got a little bit over. So we covered drainage versus water engineer part. We looked at Signal 5. We looked at a bit of climate change, a bit of aging infrastructure, Scala, some of the tools and some of the advancements. Thank you very much for listening. And if anybody's got any questions, please keep this up. Please ask away.
We've got one online to start with.
Yes, Brian Painter asks, he's interested in the views on drainage that has been installed relatively recently or historically, and the impact of new overhead lines and that may have had on drainage.
Yeah, so what generally happens is the overhead line guys go through with their big piled foundations on the big concrete foundations,
Mhm.
and they put them in where they need them, whether there's a drain underneath them or not.
Yeah.
And we quite often get crushed drains, we quite often get drainage that's just completely severed. For some reason, when it happens, the drainage guys don't always get told about it, which is very useful. And then you start to get wet beds, then you start to get problems. There is some of that outside Paynton at the moment, where we've got historic drainage with just foundations straight through the top.
You're a lot of healing and ways of doing that.
Yeah, Brian's involved with they're trying to remedy that, so
Yeah.
that's what he's.
So yeah, it's a huge problem. It is getting better.
Yeah.
The new drainage is obviously very simple to spot. It's the historic drainage where you've got hidden catch bits, so you do not know it's there till you start digging. By the time those guys put the spade in the ground and start digging, it's designed, it's built, it's manufactured, it's on site ready for installing. They're going to install it whether they find a pipe there or not.
Hopefully, Brian, we've conveyed the question that we were after.
Right, any more questions in the room?
No, thank you. We were discussing before the meeting, and it started quite innocuously about talking about bits of track in Swansea. But where you have railways in cuttings, historically, the engineer would have designed a grip drain at the top of the cutting to intercept any water from the neighbouring farmer, and he would discharge that one way, and he might then have installed a drain in the tracks of it.
Yep.
One of your earliest diagrams, and I think you're going back to it,
I'll try it.
is looking at exactly that. And really the question is, what's the preference today? Because a drain at boundary level is incredibly difficult to maintain.
Absolutely.
Railway where we don't care about the trees growing, really.
No.
We certainly don't mow the grass, as we did when those initial railways were designed. So that's the answer.
It is in some cases, it's not in others. It depends on how that water, if you've got a general gradient coming towards the railway, and then we've got a cutting as we have here, then absolutely a crest drain, or a crest ditch probably now is the better way, it captures more water, is probably the preferred option. However, if you've got a single river that's coming in here, or a single watercourse that's coming in, and that's when that floods, it expands, then actually what you might have is some sort of formal head wall to catch that water as it comes down, and you'll maybe build walls or something that actually direct that water to that head wall to actually take that, because you know it's floodable, you know it's watercourse, it's a single point. You get springs coming through, so as the water level soaks into the ground, you get springways, which is where your counterflow drains come in on the slope. They're installed more and more nowadays. They've got a reach of about 5 metres either side. So if you put one here, you'll put one probably 10 metres away, and it's going to quite dry that slope. Difficulty is trying to connect these things into your track drainage. And as with all drainage everywhere on anything, your outfall is key. And if your outfall is not big enough, it doesn't matter what you do up here, it's going to flood. You can have the biggest pipes in the world, the best drainage system, but if you've got an outfall that's that big, it's going to flood.
It's probably a typical software tunnel. Yes.
Yeah.
There's no way to get rid of the water still once it's collected there. Yeah. So, right, any more questions? Thank you.
With regards to the Scour.
Yeah.
Is there anything that you look to put in to reduce it? Or is it all about just monitoring it?
There's lots of things you can do to make it go away. So you can use rock arming, it's concrete mattresses, you can use all sorts of things. We're being pushed more and more by the consent authority to do softer engineering approaches and actually only protect the element that is at risk. So what I mean by that is if you've got a multi-span structure and your modelling shows that Pier 1, for example, is at risk of scour, at high risk of scour, and the others maybe medium risk, you would only be allowed to protect that single element. You wouldn't blanket protect the whole structure now. That's where the CFD modelling comes in, because you can actually put that protection into the CFD model and see what the effects are. Because it might be that you've protected this with, let's say, sheet piles around it. that might actually transfer the risk now because of the change in flow dynamics. You might actually have caused a problem downstream to a riverbank, or actually to our structure, or a highway structure that might be further down or further back. So yes, there's things you can do to prevent it. There's softer engineering, so you could use things like frond matting. Kevin's used frond matting. Best way to describe a frond mat looks like scaffold tubes that are weighted with torn up Sainsbury's carry bags that look like lilies. It's the best description I can get. I promise if I put a picture up, you'd go, oh yeah, I see what you mean. What that does, it tries to replicate natural vegetation within the watercourse. And you're trying to slow the water down because when scour's happening, you've got a muddy water, you've got sediment suspended within that water because of the energy. If you can slow that water down, the sediment becomes too heavy, it drops. So those are kind of a real soft engineering way to try and slow that water down and drop the sediment out before it leaves your bridge area. Or you try and capture the sediment that's coming in because it's a bit of a conveyor belt during a flood. It's not just happening out of structures. So you kind of catch that and try and drop it in and infill your own scour. There's a myriad of things that you can do to try and combat it. Once it's there, it is possible to fix. It's not turn off the bridge.
No, I think the emphasis used to be on sort of hard engineering solutions. We put a concrete slab in the riverbed, or we put rock armour in, whatever. But as I said, this whole concept of the looking at it in its wider context and the environmental issues you can cause means that you do other approaches and now.
The frond matting is down in Gorgon Pool in West Wales, and it's we've been monitoring. It was put in about 2 years ago now. We've been monitoring that, and the bed levels are rising. So the deeper the bed level, obviously, the more protected
It's actually collecting material as the vegetation would do. Yeah.
Just trying to find you some. Here's one I prepared earlier. This is one of my scour presentations. So bear with me. Yes, so let's not talk about them. Let's just skip on them. Sure, in here somewhere I have. Here we go. So things you can use: rock armour. We've all seen rock armour to protect from scour. You can use rock rolls. So these are the way that rock armour is designed is that you work out the velocity in the watercourse. You work out what's called the Shields value, Shields equations, which is the amount of energy required to lift a particle out of the way. You make sure your block is bigger than that, and it means it's not going to move during that flood event. The rock rolls are not sized like that at all. They're just small gauge rings, basically, and they are very small materials. So if they get damaged by a bit of debris coming down, they're no good. So please don't use them. This is a concrete mattress. It's a big Hessian sack that's stitched around your structure, and then one end of it's plugged into a concrete pump. It fills it with concrete, it sets, and it becomes a very solid structure. The reason it looks like a mattress rather than a flat surface is because you want that turbulent flow. You want to slow the water down. If it's got a flat, smooth surface, the Manning's value is so small that the water skims across it. And I'll show you what that looks like in a sec. So when you've got this here, where you've got a flat surface, the water skims across it. I wonder if I've got the picture of. I have a picture of Mill River. Do I have it? Bear with me. Oh, there we go. There's Mill River. So this picture here, what we've got is you've got a watercourse that comes down, turns around, and is concrete invert. And you've got what's called a transition material. At the end of a concrete invert, you should have some stone. As the water skips across the concrete surface, it should slow the water down before it gets back to natural riverbed. If it doesn't, this hole here is exactly what happens.
So it's effectively created weir, haven't you, over time.
And Welsh Water get very annoyed that we've exposed one of their pipes that used to be buried. That's what happens when you don't design it properly.
River bridge, at the road bridge, if you're in that forest like that, that's got effectively a waterfall up down the street.
And that's transition material. So you have a metre or two worth of rock that slows the water down after it's skipped across that smoothing. We don't tend to put concrete inverts in now because of the damage it actually causes. But yeah, there's a few different things you can do to combat scour. If you're really bored and you want scour presentations, let me.
come back to that. Be careful what you wish for. Okay, does that answer your question? Yeah. Okay, any other question? Any other questions? Any more online, James?
Alan Whiston just mentioned, in connection with Brian's earlier question, that we also need to consider troughing, especially raised troughing for high voltage, as it's often been installed in the drainage ditches.
Yep.
As it's the only easy location between the toe of the earthworks shoulder.
Yes.
So
Yes.
constrained areas and lots of assets fighting for the same space.
Absolutely. And what you'll find is the cable troughs make great drains as well.
Yeah.
So they fill with water and transfer water brilliantly. Right? Not that we don't tell them anything, but yeah, they're great drains.
The word used there is holistic approach.
Absolutely, yes. We'll use anything to move water around the railway. It's fine.
Good. Right. Any more questions?
Stunned silence. That's
Well,
what I like. Yeah.
Right. Well, thanks very much for coming down to do that. I'd like to call on Lee to propose a vote of thanks.
He's on. He's on.
Thanks, Andy, and thanks to Iain for that very interesting talk. I think historically, drainage has always been seen as the poor relation of railway infrastructure, and perhaps in the past hasn't been given the attention and the resources that maybe it should have. So it's really good to see that there are teams in place now and systems in place to analyse the whole cycle of drainage, where the water comes from, how we manage it and where it goes, and also predicting how things are going to change in the near future and in the medium term. So that's been a very interesting update on where we are in the railway system with regard to drainage. And I'd like to ask everyone in the room, at least, to thank Iain in the usual way, please.
Thank you very much, Iain.
Right. So a couple of more things before I think. First of all, is there any comments on the minutes of the last meeting or anything? I think that's a true record.
Yeah.
Yeah. Okay. So our next meeting, we've got Craig Fisher, who's the head of performance locally, talking about operational performance. Should be an interesting subject. Yeah, there's always an interest, a bit of tension between ourselves and the operators, the engineers and the operators. So I'm sure that'll be a really interesting talk. And if anybody else go, we'll probably adjourn to the Prince of Wales afterwards, then we want to come on for time. Otherwise, there's no more business. I declare the meeting closed. Thank you very much.
Yes.
Right. Very good. Thank you very much.